All right. Next up, we have Professor Edwin Kite, who's a prominent researcher at the University of Chicago, who has pioneered a novel approach to terraforming Mars. Working with teams from Northwestern University and the University of Central Florida, Professor Kite's team has developed a method to suspend iron or aluminum nanorods in Mars' atmosphere, creating essentially a greenhouse effect that warms the planet. This warming could release potential carbon dioxide from the ice caps, thickening the atmosphere and further raising temperatures, potentially reviving Martian streams and lakes. Everybody welcome Professor Edwin Kite.
Thank you for that introduction. Hello, everyone. I'm very happy to be here. Mars rovers and climate modeling of the past, but today I'd like to talk about possibilities for Mars's future. So the Mars rovers are exploring the traces of arguably the greatest known environmental catastrophe, which is that Mars once had rivers and lakes and a habitable climate, at least intermittently, but lost it. So on the left, we see the large valley networks that David Catling mentioned in his talk. And on the right, we see one of the rover field sites, a river delta and lake deposits. So Mars also had rivers in the past, so much warmer than it is now. But Mars today is too cold for life. So this is the basic obstacle to establishing a photosynthetic biosphere on Mars. So I'll focus on that first step in today's talk, warming Mars up. This is a necessary first step, but it is insufficient for habitability. A warm Mars with some liquid water would still be a hostile environment, even for extreme life, because of the simultaneous challenges of high ultraviolet light, salty soil, perchlorates in the soil, low pressure, which by itself is not a problem. There are dozens of species of extremophile organisms that can grow at 7 millibars, but it's still a stressor. And any pioneer organism would have to deal with all those stresses simultaneously. I'm not going to talk about those problems today, but if you're interested in that step, then you can either read the proceedings of the April 2024 Pasadena Mars Terraforming Workshop, which are online, so just Googling Mars Terraforming Workshop proceedings will bring it up. And if you're interested particularly in the pioneer organism step, then take a look at Pioneer Labs. It's a new focused research organization based in San Francisco, which is working on that. Okay, so that's the context, but I'm going to focus almost exclusively on the first step today, which is just warming up the planet so simple life has a chance. And of course, this has been an area of investigation for over 50 years. So Carl Sagan in 1971, and then in more detail in 1973, suggested adding some dark substance to the polar caps to release carbon dioxide, perhaps set up a rapid release of carbon dioxide to make Mars's atmosphere thick again. And as early as the mid-1970s, NASA was sponsoring studies to essentially look at all of the steps from the previous slide. So not just warming Mars up, but also establishing a photosynthetic biosphere, raising the oxygen level, and so on. And so if you look at the history of studies on warming Mars up over the last 50 years, you can sort of put it on axes of how easy do people think it is versus time. The first probe showed a planet that superficially resembled the moon with a tenuous atmosphere. So that's sort of the first trough, Mariner 4 in the 1960s. And then calculations by Chris McKay, building on work by Carl Sagan, showed that Mars could be close to a tipping point that would release abundant carbon dioxide back into the atmosphere, which sounds good. And then Mimi Gerstel and later Margarita Marinova showed that super greenhouse gases, for example, chlorofluorocarbons, could warm Mars. So the optimal cocktail of super greenhouse gases to do this, you need about 40 billion tons in the atmosphere. So that's a big industrial effort. And part of their motivation was the idea that if you did that, then natural release of carbon dioxide would take you the rest of the way. However, Joukowsky and Edwards underscored in a 2018 paper, and this is consistent with, David had a slide on this, that the tipping point idea, which had motivated a lot of the early work, doesn't work. And the problem is that there just isn't enough carbon dioxide stored as ice on Mars to make it work. The polar caps are mostly water ice, not carbon dioxide. There is some carbon dioxide in the polar caps, but only enough to double the atmosphere, not to thicken it to the hundreds of millibars that you would need for carbon dioxide alone to produce a warm Mars. But recently things are looking up, thanks to a local warming study by Harvard and JPL, and our own global warming work, which I'll now describe. So for this audience, you probably already know that Mars's polar caps have at least enough water for a 30-meter global layer spread out evenly, and that about 1/3 of Mars's surface has shallow buried water ice. That shallow buried water ice extends equatorwards to about 40 or 50 degrees. There is circumstantial evidence for water ice at lower latitudes, but basically no proof. And so the necessity is not just to warm Mars up to 273 K. Actually, temperatures measured by Curiosity rover and on the Curiosity science team do get on to up to 273 K, but there's no water ice there to melt. And so you need to warm things up to 273 K where the water ice is, which is, as shown by this impact, a little bit in the subsurface, polewards of 40 or 50 degrees in both hemispheres. And we have pretty good maps of the distribution of this water ice from indirect means like neutron spectroscopy and gamma ray spectroscopy, confirmed spectacularly in some cases by geologic exposures of the ice in the aftermath of impact. So those little chunks of ice don't last long, they sublimate away in the dry air. So previous work on warming Mars globally emphasizes greenhouse gases. What this plot shows is output from a three-dimensional calculation, not by me, by Isabelle Descartes, using Chris and Margarita's optimal cocktail of greenhouse gases. So the red curve is about 30 Kelvin warmer than the baseline. So that's the point at which you start to melt the ice during the warm season, which is perihelion season. Mars's orbit has an eccentricity of 0.09, and so at perihelion season, you get about 40% more sunlight than at aphelion season. Okay, so to do this, you need about 1 kilogram per meter squared column of added gas. So that's not bad. These are potent greenhouse gases, but 1 kilogram per meter squared multiplied by the surface area of Mars is about 100 billion tons of fluorine. The gases are mostly fluorine. And there's not much fluorine in the Mars soil, and we don't know of any concentrated deposits. So we're in the regime of, well, you can warm Mars, but first you have to mine much of Mars down to depths of hundreds of meters or more. And if this is the best we can do, then warming Mars is essentially still science fiction, a problem for future generations and not for the people in this room right now. We asked, can Mars be warmed with aerosols instead of gases? This is a fairly obvious idea, so it's probably been thought of before, but I haven't been able to find an investigation of this that predates our team's work. I'll now describe results we published yesterday in Science Advances. The paper is open access, you can read it all. This is the first paper from our collaboration. The lead author is Samena Ansari. She's an electrical engineering PhD student at Northwestern, working with Professor Huma Maseni. Northwestern did the nanophotonics. I did the 3D climate modeling with significant help from Dr. Liam Steele when he was a postdoc in my group. And Professor Ramses Ramirez at the University of Central Florida did 1D climate modeling as a cross-check on the 3D results. So I'm going to talk through the principle of using aerosol to warm Mars using natural dust as a starting point. But natural dust actually cools Mars. So let's talk through how this happens. So the Mars sky is always dusty. And due to its small size, natural dust is lofted to high altitude, tens of kilometers, and it's always visible in the Mars sky. It's actually present up to 60 kilometers altitude. So the top panel, that sigma subscript x comma r, is the total cross-section for a single dust grain. The sum of the scattering and absorption as a function of wavelength. So that is the solid line in the top panel. The dotted line in the top panel, that's just the scattering contribution to that. So the distance between the dotted line and the solid line is the absorption contribution. So Mars dust blocks sunlight at short wavelengths, so less energy absorbed from the sun. But in the infrared regions, which is off to the right in the pink band, that's the wavelength range within which most of Mars's thermal infrared is emitted. Mars dust lets the infrared escape. So it doesn't look like much, but that's a log scale. So the lower on the right side is a big difference. So the net effect is to cool the planet. So the key wavelength ranges for cooling Mars again are the pink band on the right, corresponding to the peak black body emission from Mars's surface. And so we need to reduce that cooling using a greenhouse agent that stops the thermal emission from just leaking away to space. Mars has a lot of natural CO2, 180 kilograms per meter squared column of atmospheric CO2 gas. And that does a good job at blocking the thermal infrared from leaving in the gray band. But you can see that the pink band is wider than the gray band. These are called spectral windows. And in order to warm Mars, we need to block those spectral windows, which are roughly 22 microns and 10 micron central wavelength. So the bottom panel just describes whether the light that is scattered is forward scattered or isotropically scattered. So if it's forward scattered, that's 1. And so that happens at short wavelengths. And at short wavelengths, you want forward scattering if you want to warm Mars up, because that means that the sunlight gets bounced down to the surface rather than being bounced back to space. At long wavelength, you actually want the scattering to be isotropic, so 0. And the reason for that is that you want as much as possible of the infrared radiation to be bounced back to the surface, keeping it available to warm Mars. Okay, so ideally you would want an artificial aerosol that looks like this, one that lets sunlight in. So this is just an ideal aerosol, blocks the infrared and forward scatters sunlight to the surface. So to test various candidate aerosols, we used three-dimensional finite difference time domain simulations of the interaction of the light with the particles. The particles are tumbled by Brownian motion. These are not active particles. They're just inert. You release them. They do their thing. Eventually, they break down in the natural environment. They'll be tumbled by Brownian motion, and so we had to calculate orientation average properties. And very quickly, just starting with a half wavelength metal dipole, we found nanoparticles that have the desired properties. So this is an example for 9 micron long iron nanorods. Aluminum nanorods behave similarly. They settle much more slowly than dust. So you put them in the air, they're swept up by natural winds. They take many years to settle out. You may ask, why is it 9 microns, not 11 microns? And that's related to losses within these particles. They're much, much smaller than the antennae we're familiar with from radio. And so analytic approaches don't work well for thinking about what the right lengths are. So the basic idea is release these particles probably during the daytime, because that's when the winds are, when the convection is strongest, so they're lofted to high altitude. You need to release them a little bit above the surface, but 10 meters above the surface is fine, and 100 meters above the surface is probably optimal, so a relatively short pipe. Then they're swept by natural winds across the planet. They have a lifetime in the atmosphere of a few years. They will eventually degrade, oxidize, break down. And so you need to keep resupplying them. There are possible loopholes to that statement. Photophoresis might allow self-lofting of the particles, and that's one possible avenue for future investigation. So here are the average surface temperatures during summer from a 3D climate model with 160 milligrams per meter squared of nanorods. So basically everything except the yellow is, everything is orange, red, or pink is above the above 273K, including most of the ground ice zones. And this is the average temperature during the summer, which I've defined fairly arbitrarily to just be the warmest 70 sol period during the year. Day-night average, but it's still, this is not the annual average temperature, which remains colder. Okay, and so this corresponds to about 30 liters per second, assuming a 10-year particle lifetime, which is probably about right. So this is the seasonal cycle in the control simulation on the left and in the warm simulation on the right. So this is just to illustrate that it's only warm during the summer in this case. This is roughly the threshold of nanorotor loading at which things get interesting for allowing liquid water on Mars. But of course, there's no limit on adding more nanorodors in principle. And so this shows the global mean surface temperature as a function of nanorotor loading. So there are a few takeaways from this plot. What I showed you on the previous two slides is the black arrow. And so this is 5,000 times more effective on a per unit mass in the atmosphere basis than the best greenhouse gases. Because the x-axis is milligrams per meter squared, right? Whereas the previous best was 1 kilogram per meter squared. We've only just started looking at aerosols. So this is the sort of, these are not optimized aerosols. And that comparison is comparing to the optimal mix of greenhouse gases. Other takeaways, there doesn't seem to be any in-principle barrier to getting to 273 Kelvin, but you can see that the x-axis is a log scale, whereas the y-axis is a linear scale. That's a very common attribute of like greenhouse agents, either gases or aerosols. So it does get harder and harder to warm as your desired temperature increases. But then the flip side of that is that you don't need a lot. If you just want 1/3 the warming as a test or precursor, then you only need roughly 10% of the infrastructure. So that's the log linear scaling working in your favor. Okay, yeah, so at about 10% loading, you already get about 1/3 of the warming. I think I'll skip this slide, but this is in our paper, which is open access. So this is the detailed vertical distribution and atmospheric thermal response. This is the first paper, and we're continuing to work on many other angles. So the obvious one is optimizing the particle design. So I'm confident that we can get at least a factor of several improvement beyond what we published yesterday, but I don't know how much more beyond that we can do. One totally different line we're pursuing is carbon nanoparticles. So carbon nanoparticles are attractive because graphene, for example, which was fairly recently discovered, was actually fairly recently popularized. It was actually discovered by Soviet scientists in the 50s, 60s, but no one paid attention. Has a 0.77 milligram per meter squared density, and so it's an attractive particle for warming Mars. We're investigating that. Thinking more about climate feedbacks as Mars warms. Right now, our models do not include carbon dioxide outgassing from the poles, but we're sure that would happen, and so that's an obvious additional effect to include. And water vapor buildup as well, because water vapor is a strong greenhouse gas. And we also want to do zoomed-in simulations, essentially weather modeling rather than climate modeling, of exactly what happens at the release point, because you have a very concentrated release of warming particles. And so what does that plume do? Manufacturing, for metals, one possible pathway is molten regolith electrolysis followed by physical vapor deposition with roll-to-roll processing. Then you've got to detach them from the roll and then release them. Key issues with this approach will be consumables. So if you're doing molten regolith electrolysis, you want your cathode and your anode to last as long as possible because your replacements have to be shipped in from Earth, and coatings on the particles. And many organizations are looking at this, including Blue Origin. For both the metals and the carbon case, you're looking at about millions of tons needed in the atmosphere at any one time. So it's still a large amount, much smaller, of course, than metal production on Earth, but still a large amount compared to everything we've done for in situ resource utilization beyond Earth. And so millions of tons for a 10-year lifetime would be hundreds of thousands of tons per year, sustained indefinitely. So for carbon, MOXIE, which is an instrument on Perseverance, the rover that David Catling is associated with, electrolyzes carbon dioxide to make oxygen. With a small change in voltage, it can make carbon as well. And that can be used as feedstock for top-down synthesis of carbon nanoparticles, then ultrasonication for size sorting, further selection probably needed to get just the right sizes that you want because the resonant wavelength will depend on the size, and then release. An attribute with these particles, by the way, is that they're probably going to be only about 1 micron across. A little bit counterintuitively, graphene and related products resonate with thermal infrared at micron or submicron sizes. And so key issues and needs for this approach will be efficient selection of just the right sizes, and again, coatings. And for this audience, so you need a particle making system, a terraforming engine, to be sent to Mars. So SpaceX's Mars rocket, Starship, makes its 5th flight in a few weeks. And in April, SpaceX released their plan for Mars. It says Starships will send 250,000 tons to Mars every 27 months. So SpaceX has almost finished building a factory, shown here, whose purpose is to build 1 reusable Starship every 2 days. I don't know if SpaceX will get to the numbers shown here, but this is much more than you need to get a terraforming engine to Mars, and so we can do it from a logistics perspective. Okay, so what are the next steps? Simulation, we are designing much improved particles, we are studying weather modeling of plume release, and we need modeling for climate feedbacks. Batch manufacture for testing, we need to validate the simulated optical properties. We need flow tube measurements to measure clumping, and wind tunnel experiments. And this is building towards a precursor or test mission. Monitor the plume, measure the warming. And all of these will test assumptions. So clumping behavior, reuptake, plume behavior. So if things look good, then the next step will be to warm Mars by about 10 Kelvin. So why that number? It's much bigger than interannual variability, but it's still much less than you need to generate liquid water. And so the goal there will be to assess the size of natural climate feedbacks. And then finally, the final step would be full deployment, starting to melt the ice. And the assumptions that are tested there are just unknown unknowns. And so a nice attribute of this method is that if you stop releasing the particles, then the climate just goes back to the pre-perturbation state within a few years, because the particles just settle out. Okay, advocates of terraforming must first become advocates of scientific exploration of other worlds. If we're going to seriously contemplate warming Mars, we have to confront big remaining uncertainties. And in my mind, one of them is whether Mars has liquid water aquifers deep down. We just don't know. A good method to search is electromagnetic sounding. In my mind, that's a priority, both from a scientific perspective and also looking ahead from a warming Mars perspective. We know there's 30 meters or so global equivalent layer of water sitting on the surface, but we don't know how much global equivalent layer of water there is deep underground. And if they exist, we must check if they have extant life, because study of that life could have great benefits that would warrant robust protections for its habitat. So zooming out, this is my last but one slide. We don't know that Mars has the volatiles that would be necessary to produce an atmosphere breathable by humans. But we do know that Mars has enough volatiles to produce an atmosphere that could support photosynthetic biosphere and plant life. And so, not my metaphor, but quoting from previous paper, as you warm Mars up, it's a little bit like descending a mountain. So Mars today is colder than the coldest places on Earth, uninhabitable for life. But as you warm things up, you enable more and more complicated photosynthetic life. And so I'm sort of out of time, so I'll just summarize. I've talked today about warming Mars to enable a photosynthetic biosphere. Recent developments include flight test success for Starship, which improves our ability to land payloads on Mars by about 2 orders of magnitude per Mars landing. Aerosols offer 4 orders of magnitude improvement on previous proposals for globally warming Mars. There's a new FRO in synthetic biology for Mars, so pioneerlabs.org. And if you're interested in the big picture context, then I encourage you to check out the proceedings from the 2024 Pasadena Mars Terraforming Workshop, which are online. Our own next steps are focused on batch manufactured lab tests of the nanoparticles. Thank you.
Okay. Time for one or two questions here.
Thank you. So I read about this story. It made the news. It's pretty big news a couple days ago. They named it Glitter. They called it Glitter. Is that what you guys came up with, or was that more the news that came up with the glitter? The one question I had was the difference between the aluminum and the iron. Is there going to be a big difference in the raising of the temperature?
So our paper is open access, so I'd encourage you to read the paper. I have no control on what happens some steps down the chain when reporters get to it. The difference between the iron and aluminum from a radiative properties perspective is small. Aluminum's advantages are it doesn't oxidize as quickly. It's lower density, so less mass for the same radiative warming, and less clumping concerns. So overall, we think aluminum is better. Is that the question? Okay.
If you have metallic nanoparticles in any concentration, would that block all radio communications?
So Mars already has an ionosphere, even though it has no magnetic field. It doesn't have an ionosphere. No, the wavelengths are very different. So laser communications are probably the way things are going anyway.
Thank you very much. We're going to, thank you very much.